Hello everyone, this is Chandrasekhar Kumar. I have been teaching physics for 14 years for IITG Main and Advanced and NEET examinations. Here we will discuss simple harmonic motion with some PYQs of IITG Advanced and NEET. So let's start simple harmonic motion, that is SH. SH means simple harmonic motion. So if a motion is periodic motion, that is, if a motion is periodic motion means if the motion repeats itself after a fixed interval of time. Also, if the motion is to and fro motion, the motion is also to and fro motion, that is oscillating motion. To and fro motion means once the motion is towards the mean position, again from the mean position, towards the mean position, from the mean position, again towards the mean position, and from the mean position. Then such type of motion is called to and fro motion. And also if the acceleration of the body, that is A is proportional to the displacement from the mean position, and the direction of the acceleration is opposite to the direction of the displacement from the mean position, that is, here we have to put here minus sign because the direction of the acceleration of the body is opposite to the direction of the displacement from the mean position. So if these three conditions are satisfied, then we can say that the motion of the body is simple harmonic motion. For example, suppose that this is a smooth table and this is our fixed support here, and this is a spin mass system. Initially the spring is at its natural level. Now if we pull this mass for some extent, suppose that x, and if we will pull it here, now if we will just leave the mass here, then it will move towards the mean position, that is here x equal to 0, this is the mean position. Then the body will move towards the mean position, that is x equal to 0, and after reaching the mean position, it will move away from the mean position, that is from the mean position. It will again come here, that is from the mean position. This is towards the mean position, this is from the mean position. Again after reaching here, x equal to a, x equal to here, we can say minus a, then it will again move toward the mean position. So again the motion will be towards the mean position, and again it will reach to the mean position, then after reaching here it will move from the mean position. It will from the mean position. So in this way the mass will move in to and fro motion, that is oscillating motion. And here we can say that if the body is pulled here, then the spring will pull in the left direction. So at this point the direction of the acceleration is leftward, but the displacement is rightward. So we can say that the direction of the acceleration is opposite to the direction of the displacement from the mean position. And if we will pull for more aspect, that is if x will be more, then a will be also more. It means the acceleration is proportional to the displacement from the mean position. So here all the three conditions are satisfied. So we can say that the motion of the mass will be, in this situation, simple harmonic motion. So now we proceed this expression. So A will be equal to minus omega square x. Here omega is called angular frequency, that is 2 pi f. F is the frequency and omega is the angular frequency. We can also multiply it with the mass of the body. It will be minus m omega square x, and it will be force is equal to minus m omega square x. This force is responsible to move the body in such a way. So it is called restoring force. It is called restoring force because the force is responsible to move the body towards the main position, and this force always acts towards the main position, and also acceleration always acts towards the main position. We can also write it as F R is equal to minus kx. We can write here equation number 1, equation number 2, equation number 3 in this way. We can also take here magnitude. So the magnitude of Fr will be m omega square x. We can also write F R is equal to kx. Here F R is the restoring force. Now we will take a question which was asked in IIT 2024, and it is based on the question. So let's solve that question. In this question, there is a hoop and it is neutral and it is uncharged. Also, it is frictionless, and there are two beads of mass m, each of mass m and each of charge q. One bead is fixed here, its mass is m and charge is q, and another bead is present at diametrically opposite end here, and this bead is free to move on the hook. This is the center O. Now if this bead is displaced from its position for a small distance x or a small distance x, so bead will be here. And if the bead will be left from here, from this position, then it will oscillate in SHL. So we have to determine the square of the angular frequency, that is omega square. What will be omega square? Here R is given, R is the radius of the hook. So let's start to solve this question. Here we can join these 2 points. Now this is the first one, this is the second one. So the force acting here, this is the force, and this force will be electrostatic force Fe. Suppose that this angle is theta, then this angle will be theta by 2. Also this angle will be theta by 2. This is also theta by 2. We are drawing here at this point the tangent. This is the tangent. This will be 90 degree. This is the radius, this is the tangent, so this will be 90 degree, 90 degree, and this will be also 90 degree. This is not this angle, so this angle will be equal to 90 minus theta by 2. Therefore, the component of this force, electrostatic force, in this direction will be F E sin theta by 2. Now, if this displacement will be smaller, then this force F sin theta by 2 will act towards the mid position, that is towards this point, and this force will be responsible to move the charge Q, this is the small charge Q of mass in simple harmonic motion. So this force will act as restoring force. Therefore, restoring force will be equal to Kx, and here this restoring force will be equal to F E sin theta by 2. And F is the electrostatic force, it will be equal to Q square upon 4 pi epsilon naught into distance between these two charges. So this is R, this is R. So the distance between these two bits will be 2R. 2R cos theta by 2. This is 2R, so it will be equal to 2R cos theta by 2. So here the distance square will be equal to 2R cos theta by 2 whole square. This is the electrostatic force, and this will be sin theta by 2. So for a small value of, since x is very small, so theta will be also small. So when the theta will be small, therefore theta by 2 will be also small. So for a small value of angle, we know that sin of the angle will be equal to angle. So sin theta by 2 will be equal to theta by 2. Therefore it will be equal to Q square upon 32 pi epsilon naught cos square theta by 2. And here theta, again this is theta, we have already multiplied 2 with this theta. So Q square 32 pi epsilon naught. Now for small angle, here theta by 2 is small angle, so for small angle theta by 2 cos square theta by 2 is equal to 1. So we can write here 1 in place of this, and theta will be equal to x upon r. So we can write here theta is equal to x upon r. Also there will be r cube here, so r square. So 32 pi epsilon naught r square x upon r is equal to q square x 32 pi epsilon naught r cube. Now we can compare it with this equation. So we can write here f r is equal to this and f r is equal to kx. Therefore K will be equal to Q square 32 pi epsilon naught r cube, and we know that K is equal to m omega square. Therefore Q square upon 32 pi epsilon naught r cube. So omega square is equal to Q square upon 32 pi epsilon naught r cube. So this is the answer. So in this way we have solved this question by assuming this motion as simple harmonic motion and linear simple harmonic motion, because we have taken here x as linear displacement. The bead is displaced by some linear displacement x, therefore it will be linear simple harmonic motion. Now we can also solve this question by assuming it as angular simple harmonic motion. So we will solve this question by assuming it angular simple harmonic motion. So we will discuss here angular simple harmonic motion. We will write the answer here. Omega square, we have omega square as q square upon 32 pi epsilon naught r cube. Now we will solve it by considering it as angular SHM. In both the conditions, the value of omega square will be the same. The expression of the omega square will be the same. So here we can see that this is the force acting on the bead and this is the R vector. This is the R vector. So the torque will be, in this case, generated torque acting on this bead, and this torque will be responsible to move the body in angular simple harmonic motion. For angular simple harmonic motion, the restoring torque R can be given as k theta, and here restoring torque R is equal to I omega square. I omega square theta. So if we want to determine omega square, then at first we have to determine here restoring torque. So here the restoring torque will be equal to R cross F. So here R, F, E and sin theta by 2. R, F is equal to q square upon 4 pi epsilon naught. Distance square means 4r square cos square theta by 2, and this is sin theta by 2. Sin theta by 2, for small value of theta again, sin theta is equal to theta, so we can put here sin theta by 2 as theta by 2. Therefore it will be equal to q square upon 16 pi 32 pi epsilon naught R. For a small value of theta by 2, cos square theta by 2 will be also 1 into theta. This will be equal to q square 32 pi epsilon naught R, and here theta we can write here for R equal to this. Now we will compare this equation to this equation. So I omega square will be equal to q square 32 pi epsilon naught R into theta. Also theta is here. Therefore, omega square is equal to q square upon 32 pi epsilon naught R I. Omega square is equal to q square upon, and I is equal to, here I is equal to mr square, so 32 pi epsilon naught R cube into mr square. Today here I is equal to mr square. This mass m is rotating about point O, distance r. So the I will be, at the moment of this I will equal to I is equal to mr square. Therefore, we have the expression again omega square is equal to q square upon 32 pi epsilon naught r cube. So we can see that both the expression for omega square are the same. So in this way we can solve the same question in two methods. In the first method we have considered the motion of the bead as linear simple harmonic motion, and in the second method we have considered the motion of the bead as angular simple harmonic motion. In both the conditions we have the same expression of omega square, that is omega square is equal to q square equal to pi epsilon naught r cube. Now we will take another question. This question was asked in NEET 2023. The question is that this was question number 1. This is question number 2. The question was that the graph is given of the displacement of the body against the time. The body moves in SHM. Along y-axis we have taken the time, and along x-axis we have taken the time, and along y-axis we have taken the displacement of the body. The graph is given like this. This is 0, this is 2, this is 4, this is 6, and this is 8. Time is in second and displacement is in meter. This distance is given as 1 meter. So here the question says that what will be A at t is equal to 2 seconds, A is equal to what? So we have determined A, that is acceleration of the body at t is equal to 2 seconds. So we know that A is equal to minus omega square x. So minus omega is equal to 2 pi square into x. Minus here, we can write here, see here, we can say that this is a complete oscillation, and the time taken by the body in complete oscillation is 8 seconds. Therefore, we can write here time period is equal to 8 seconds. So it will be minus 2 pi into upon 8 square into x. This is equal to minus pi square upon 16. And here x will be equal to, we have determined acceleration at t is equal to 2 seconds. So at t is equal to 2 seconds, x is 1 meter. So we have to put here x is equal to 1 meter. So the answer is minus pi square upon 16 meter per second square. Now we are taking again one question which was asked in the advanced 2018 based on SHM. This was asked in NEET. Now this is the third question. The third question was asked IIT Advanced 2008. And the first question was asked in IIT Advanced 2024. This is the third question. In this question, it is said that there is a container or bucket, you can say, and there is a liquid in this container, and a spherical ball is dipped here. here the half part of the spherical ball is inside the liquid and half part of the ball is outside the liquid. The radius of the ball is r. The radius of the ball is r. Rho v is the density of the body, that is ball we can say, and rho L is the density of the liquid. Now this ball is gently pushed for a small extent x. It means when it gently pushed downward, then some part of the ball will be immersed inside the liquid, like this. This is part x. This is the x, the body, that is the ball will go inside the liquid for extent x. Then this will provide, that is the body will provide to the ball in the upward direction the access point force. This access point force will be responsible to move the body in access. So this access point force FB will be equal to, this portion is inside the liquid. The formula for the buoyant force is rho of the liquid, volume of the liquid, which is inside the volume of the body, which is inside the liquid, that is V. So rho L and pi r square x. This is the volume of the ball which is inside the liquid, Z. Now this force, that is the point force, will act as the restoring force. So restoring force is equal to denote at m omega square x. This is the magnitude of the restoring force. So we can compare this restoring force with this point force. That is, this point force will provide the necessary restoring force. Therefore, m omega square x will be equal to rho L pi r square Gx. Therefore, omega square will be equal to rho L pi r square G divided by m. Therefore, we can write that omega square is equal to rho L pi r square G upon m under root. Omega is equal to under root rho L pi r square G, and the mass of the spherical ball is 4/3 pi r cube into density of the ball. Therefore, omega is equal to under root 3 pi by cancel, 3 density of the liquid Z and 4r density of the ball. Therefore, time period of oscillation is equal to 2 pi upon omega, that is 2 pi under root 4r density of the ball upon 3 density of the liquid into C. So this is the time period. So in this way we can easily determine the time period of the ball which is moving in simple harmonic motion. So I hope that your concept is clear regarding system, and also we can derive the expression for the velocity of simple harmonic motion. Also we can derive the expression for the displacement in terms of time displacement. We can also relate the displacement with the velocity. We can also determine velocity in form of time as well as displacement. So there are so many expressions. Also we can determine the energy of the body which is moving in a system, the kinetic energy as well as the potential energy. I think that these all the questions which we have asked from ITG Advanced and NEET are clear to you.